Okay, I'll just introduce this. I will set up the sort of the system, and then we'll do the derivations and all next time. But so what goes into a pogo stick hopper? So let's just think about what are the different, like just a caricature of different phases in the movement of the pogo stick hopper. Okay, so we'll just do simulate, we'll just do a one-dimensional thing, but we'll assume that it can actually move in the lateral direction too. So if you have a hopper, and we'll put a spring inside the hopper. So it's in the air, just like the ball. It's flying in the air. Some point of time, it'll make contact with the ground. So this is going to fall as a projectile. Then it's going to hit the ground, and then probably it'll compress the leg. Then come out, and then once it comes out, it's again going to fly in there. And then it's going to be, and then it keeps going. Okay, so let's choose this point to be a very special point, this place where it is in the air. Let's say that this is the time when y dot, that's the velocity in the y direction, is 0, or it's the apex. Right? You need to be, at some point of time, you need to be have 0 speed in the vertical direction. And then let's say this point again is the same point, apex. So this is flight, flight. This phase is what we call the bounce, where the spring actually comes into play. It goes compress and let go. But then this other thing which is important, which is you need to detect when exactly the ball makes, or the pogo stick makes contact with the ground, right? So we need to detect that. So we need to know exactly when the contact takes place. And then we also need to know from here when the release will take place. That is it needs to take off in the air. So we have flight, bounce, flight. Those are the phases where we need to write the equations of motion. But we also need to figure out when exactly the ball or the pogo stick makes contact, and we'll find that condition, and when it releases. So it basically makes contact clearly when the length, when the foot, in this case, the foot is not really shown, but it's a point mass, which is here, basically touches the ground. So that's easy. But when does it take off? Well, in this case, we'll assume it takes off when the spring is uncompressed. Okay, so it's compressed, and then it's free length. When it's at its free length, what happens is the force felt by the foot from the ground is going to be 0, and that's the takeoff phase. Okay, so we need to parse all this together. As let me write this one equation, and we'll stop. So this whole thing we did was because we want to identify that repeating unit. The repeating unit here can be easily found by writing it down this way. Let's say flight, contact, bounce, release, flight. And then this flight will go back to bounce. This will come from release. So if you look at this, you can see that the repeating unit is right here. Okay, so we start at y dot equals 0, end at y dot equals 0. Let's call that one step in this case, or one bounce, or one hop, whatever you may like. This is the repeating unit. So all we need to do is simulate this one hop. And once we do that one hop, we can repeat it any number of times to get it to jump. Now, could be cases where it fails, which is something we will not talk too much here. the hopper in one dimension doesn't quite fail. But when you do this in two dimension, there'll be cases when it fails. It could fall backwards, it could fall forwards on its face, and you need to be aware of that, right? You cannot just keep bouncing if you just are crazy with your foot placement. So what we did here was try to understand what is that repeating unit. We have flight phase, which is here. Then we have to detect when the contact happens. So the contact condition is not too hard. If the leg length is L, then you know when the contact will take place. And of course, you also need to know something about this angle, right? So that angle and the leg length will tell you when exactly the bounce occurs. Then there is a compression phase. Then there's an extension phase here. And then when you go to release, when do you release? So it turns out that when the spring is fully unstretched, the force in the spring is going to be zero. That means the reaction force is going to be zero. And when the reaction force is zero, you are airborne. And once you're airborne, you go to flight and you stop. Okay, so that's the repeating unit. We've sort of got the different things. Let's try to see how to model each of these uh, aspects, right? So flight, contact, bounce, release, and flight. The last one, the flight, and the rightmost one, flight, is the same thing, the same equation. So we need to model the remaining four. So we'll write the equations for all these four different phases. Then we will go to Python and code it. Okay, and then we'll try to understand. And to make life easy, what I'll do is I'll make that angle theta, this one, as zero, so it's going to hop in place. But for the homework, I'll make you do a more interesting problem where you will basically vary the angle of the leg, the touchdown angle, and so as to make it go over obstacles and things like that. That will be more fun than what I'm going to do in class, but this is needed. It's easier case. So let's try to model each of these phases. So first is the flight phase. Okay, now for the flight phase, it's just an overkill to try to write the equations of the flight phase using what do you call Euler-Lagrange, right? Because what's the equation of a falling ball? It's basically x double dot equals 0, and y double dot equals minus g, where g is downwards. Since g is downwards and convention is upward is positive, we have this equation. So I'll not write the Euler-Lagrange here. Next, we'll see when the contact occurs. So, and I did not draw the spring because the spring is massless, so it really doesn't affect anything over here. Now, when the leg makes contact, let's say this is L, and then we are going to assume that the contact is made when the angle is theta. So this is a control variable. We've not talked about control so far in the course, but we'll get to control soon. Where you decide to step is something which you can decide, right? How far you want that leg to go. So that's a control variable. It'll actually determine how you will bounce off and move forward. So if you're given L, and then you want to find when is contact made, what is the condition which determines contact, then you can see that when L cosine theta, right, which is this y distance, is equal to 0, is when contact would be made. So when this occurs, when L cosine theta equals 0, okay, I should correct myself. So let's say that this is x comma y. Maybe this is a bad way of writing this. So let's say that we always keep track of the center of mass, x and y. Right? That's what we've done over here, x and y. So y minus L cosine theta equals 0 is when you would have contact made, right? When the vertical height, which is y, minus L cosine theta is equal to 0, the foot, this is basically the foot position, right, is equal to 0 is when contact is made. So y minus L cosine theta is the y distance of the foot, and that should be 0. Okay, that's the contact. The third one is the bounce phase. Okay, the bounce phase is when the mask undergoes well, sort of a deformation because the spring is compressed and then let go. Okay, now for this one, we could use Newton's laws, we could use Lagrange equations. To use Lagrange, we know step 1 is to identify the position velocity of the center of mass. So that is just simply x, y, x dot, y dot. The second step is to identify the Lagrangian, which is t minus v. So in this case, t is just half m, and we need to write that in terms of the center of mass. So in this case, x dot square plus y dot square minus v. So v is the potential energy, and the potential energy is going to be mgy. Okay, but then there's another force here which we need to account for, is the spring force. So the energy stored in the spring. So let's assume that the spring constant is k. So plus half k, let me just call it L minus L0 square. Okay, we need to figure that out. I can't keep it in terms of L, I need to keep it in terms of x and y. So L minus L0, where L0 is the unstretched length of the spring. Okay, so L0 is something which is given to you. It's because that's the unstretched length of the spring. What is L? L is the distance from, it's basically this distance. Okay, so let's assume that this point has coordinates xf, yf. That's the foot position. Okay, I wrote down yf only here, but it's xf, yf. So L, if you can see, it's just if you know the coordinates of this point and you know the coordinates of this point, then you pretty much know what the you pretty much know what the length is. It's going to be square root of x minus xf square plus y minus yf square. Okay, now if you are going to always make contact with the ground, then yf is simply 0, right? Because this is the ground plane. Now that's not true if you are going to step over a obstacle, then your yf will not be equal to 0. It's going to be non-zero, but in this case it's just 0. So that's your L, and now what remains is to use that in the equation and derive the equations of motion. So L is all this. Let me write that down, expand it out. Half m x dot square plus y dot square minus mgy minus 0.5 k and square of this. Okay, so to derive the equations, I go d dt. So this is a step 3. Here qj is going to have x and y. Okay, so let me just write the equations, but it's fairly straightforward to get the equations. Now you have L and Q. Okay, so the equations, there are two equations. One of them is mx double dot equals L0 minus L. Okay, so this is basically return sums of L, just so that it makes your life easy. Otherwise, it's going to look pretty shabby because L is like the square root term. And then my double dot equals A L0 minus L y divided by L minus mg. Okay, where L is square root of x minus xf square plus y square. Okay, so that was the most tedious part, but we're getting there. So we've got the equations of the bounce phase, and we're left with one final thing, which is if you go back to the pogo-stick, there's a release condition, which is basically when the force goes to 0. So let's see what that condition is. So finally, is the release. This happens when, so the force is essentially this. This is the force. So the spring force is K times L0 minus L. When that goes to 0, the spring is fully unstretched. And you got to basically switch from bounce to the stance phase to flight phase. So this happens when L0 equals L, which equals x minus xf square plus y square. So you will be checking for this condition, L0 minus square plus y0 square. So equals 0. Okay, so now that we've got different question. Yeah, bouncing the pogo stick. Bouncing ball was done last time. That was the difference being that for a bouncing ball doesn't have a spring, and this one does have a spring. That's the difference. So you'll see a K coming here, which doesn't come in the bouncing ball. Okay, so what we'll do is now that we've got this, the fun part is actually doing the simulation, I think. So when we simulate the system, similar to the pogo stick, sorry, the similar to the bouncing ball, to do the simulation, we do the following. So simulate in Python. So first thing is to identify there's this whole repeating unit. It's flight, contact, bounce, release, flight. Okay, and then we'll see that this ends at, well, this is repeating unit. It's one, you can call it one hop or one bounce or one step. And the other thing which is important is you will use this command solve IVP with equations of motion It also needs an input as to, you need to tell it, I think the initial condition. You also need to give it the time. And then there are a bunch of other parameters, like there's a spring constant, there is a mass, and so on. And then there's a function called events, which which you need to specify. Now the events will depend. So if it's going from flight to bounce, then what you're looking for is contact, meaning the length, the condition I showed you, y equals yf. When you're doing release, it's going to be, for release, it's going to be the condition that L0 is L. And then flight, you typically like to stop at the apex. So apex would be y dot equals 0. I forgot to put that maybe. So in this case, we just, yeah, so the other one, which I forgot, which doesn't have to be a condition, but let's just put that, is that apex is another condition, which I should put there. Yeah, this is the apex condition. I wrote it down here, but let me just put it down in the equations. 5. Apex occurs when y dot equals 0. That's the vertical velocity is 0. Okay, so we'll just use this for this IVP is basically, remember, equations. It's basically differential equations. There are differential equations here, here, and here. And the events, which is this condition, will be this one and this one. So when you do flight, you have equations. Contact will be an event, you stop. You apply the equations for bounce. Then if you release, stop. You apply them for flight. Then there is, I should have put it here. There is, yeah.
So this is very general, right? If we wanted to be more specific, maybe for contact, we could break it down into like the surface contact and the compression, and then the uncompression of the spring.
Yes, so you could also break down the bounce into two parts. One is the part before making contact to the lowermost point, so that will again have y dot equals 0, because it does, when you go in a curve like this, at some point when you're here, you'll have a velocity over here will also be equal to 0, because it's going up. There's a, yeah, you could break it down that way too. Yeah. Yeah, you could break it down to any number of times you want. It's not a problem. So we will actually break it down in a different way. So the reason why you might want to break it down is because you might use a different spring constant during one half and a different spring constant second half. So if you want to, say, for example, jump higher, what you'll do is you'll have a spring constant K1 here, a spring constant K2 here. And then if you make K2 greater than K1, you'll see that you'll jump much higher than what you came through. And then you want to slow down, you want to jump shallower, then what you'll do is you'll make the opposite, you'll make K1 less than K2. So yeah, that's absolutely possible. I'll show you how to do this without actually breaking it down into events. It's not the best way to do it, but you can actually put a conditional inside the ODE to make that, and we'll actually make it bounce. Okay, so that's that. This is there, we are all set. This is also the thing we need to model, which we've already written down. Let's see how to write this code. Let me just run the animation first. Okay. So pogo-stick, this is just simulating this with a foot placement angle of 0. So it's just going to bounce in place, not going to move forward. And I did set the velocity also to be 0, the horizontal velocity. This code is going to be fairly long just because you have to have so many events and you're trying to manage it. It runs 300, I think 300 lines. Yeah. Clearly, a big chunk of this is actually doing the animation. But let's see what other things go in. So I always like to define the parameters as a class. This keeps the code nice and clean. So I can call this as a parameter, and then I can pass it as a function call. Sine, cosine, animation. It's essentially just draws the dot and then draws a straight line for a given leg length. So that's about 76. It's about 220 lines of code. Okay, I said there's the basic building block is one step. Okay, that is the building block, and we need to populate that with different parts of the motion. So for example, I start with solve IVP flight phase. So this has equations for the flight phase, and in there is what he'll use. And then there is something called event. So this event is called contact. The contact event means you're going to try to stop the integration when the height is, it's leg length cosine theta. So that is defined somewhere else, but let me go through this main part first. So this is all bookkeeping. I need to do some bookkeeping in order to save the data. That is for animation. Okay, so then I go to the stance phase. Now, assuming that the ball has made contact with the ground through the spring, there's the stance phase. That's the bounce equation with the spring constant. And then I wait for release. Okay, so it integrates till release. So then there's some bookkeeping. Bookkeeping again. And then finally stance to apex. Here what happens is I do flight phase. Again, the flight phase, and the event is apex. Apex means when the velocity in the vertical direction is 0. Okay, and then there's some bookkeeping. Okay, eventually what I do is I take the data for each of those phases. So here we have T1, T2, T3. These are basically flight, bounce, T2, T3 again flight. You put it all together and then ship it back as a return argument. Okay, and then this basically goes through the conditions. I said release was L minus L0 is 0. So that's basically, this always checks for the condition that something equals 0. So here length L minus L0 is 0 is the condition. Well, L0 is x square plus y square. L0 is input parameter. So I don't have xf here. I forget why. I think it is yeah, I should have x minus xf. I think it's just that I choose to start and end at 0, and that's why I don't have it. But you need to keep track of the foot position actually and keep running, otherwise you'll give weird results. Here I check the contact condition, which is, I said, the height should be 0. So again, I need to check that passes through 0. The height is a different condition altogether. Here the velocity is checked. The velocity in the vertical direction should be 0. Then the flight phase equations are x dot 0, y dot minus g. The 0 here means that there's no acceleration in the horizontal direction. The minus g means there's an acceleration minus g in the vertical direction. I'll skip the controller for now. I'll show that to you in a bit. The stance phase, what I do is I take the spring force and then apply it to acceleration. Essentially the same thing I derived it. I just broke it down this way so it's easy to understand. Okay, and then so those are all functions, but the main code is essentially calling one step right here for 5 steps. So it just runs 5 steps in the animation. Now, as I said, when I do this, if I drop this pogo stick from a height, because the spring constants are the same, K1, I have 2 constants, K1 for the first phase when it compresses and K2 for the bounce phase, and those are the same. And I'll show you where it is. So here, K1, K2 is the same, 100, 100. So you'll see that it bounces to the same height. This is a conservative system. There's no friction losses. Unlike the elastic collision where there's E, here it's going to just bounce off back because it's a spring. Now, what I can do is to take into account that I could break down the bounce phase into 2 parts and do it that way. But what I did was this sort of a lazy way, because there's so much bookkeeping involved. I took a shortcut, which is I went to the bounce phase equations. sorry, stance phase, I call that stance, I didn't call it bounce. Okay, for the stance phase, here I chose the spring constant to be the average of the two. But what I could do is I could call a function. Okay, here is a controller, something you can use it to control. I passed in y dot k1, k2, k1 being the spring constant for the first phase, k2 spring constant for the phase. I passed in the velocity in the vertical direction to this function controller. What it does is when going down, so if y dot is less than 0, so when y dot is less than 0, it's going down, right? Because the velocity in downward direction is negative. I use spring constant k1. And when it's going up, I use spring constant k2, and I just return k. So now when I do this, and I actually change the spring constant, because now they're same, it'll have an effect. So let me increase it by 20%. So from 100 to 120. So this is going to put in more energy into the system. And clearly, when you put more energy, it's going to jump higher. Okay, you could go 150. So the height automatically adjusts. That's how I coded it.
Professor, if
Yeah.
you lower K1 to 50, will that equalize it?
It will not, well, it'll not equalize, right? It's always going to pump more energy because K2 is greater than K1. I think what happens is some point of time it just goes inside the ground. So this will fail, I think. I don't know if I've wrote code to catch this, but this will fail. Yeah, it fails because what happens is the spring is, if it's jumping from too high, the mass will go inside. But what you can do is to fix it, you can make it 500, 500. And then what I can do is increase that. So I added a bigger spring constant, so it's 500, 500, so it's going to maintain the height. But if I want to increase it by 50%, so that will be 750. It should work, I think. And you can see that it is much more stiffer, so it doesn't really penetrate. But you could, I don't know if this goes, fails again. Yeah, that works. Okay. Okay, so I'm still working on this, but I'll have a homework where, and I think this will be fun. So what we can do is actually in this also has the step angle. So you can actually project this at some angle. So you can actually change the angle of the leg, the spring. You can shoot it at a different angle, and so you can actually make it go forward. And the fun part is if you get it to go forward and bounce over obstacles, that is like the fun part. So I'll try to see if I can come up with a homework problem for that, but that will be fun to do.